Hello, gentlemen. Welcome to our video on Chapter 14 Quiz Answer Key. So use these answers here to guide yourself through reviewing your quiz since we can't do it together in a timely fashion. So question 1 says the energy diagram below represents the process of a blank reaction. So we said earlier if our reactants and products are at these points, that means I have gained some amount of energy in this journey and I've lost some amount of energy in that journey. Well, I have lost more than I've gained, so this is an exothermic reaction overall. That's the way to do that. If you had actual energy values here, you would do, final minus initial, and it would get you a negative value. So that's exothermic. Question number 2. If the rate law for the reaction 2A plus 3B goes to products, is first order in A and second order in B, then the rate law is. Now we said that the rate law has the format of this. Excuse my handwriting, guys. I know it's not the neatest. Now, the reaction orders are what you put up here. These do not depend on the balanced chemical equation. The 2 and the 3 have nothing to do with the M and the N for Chapter 14. So your rate law is going to be that the rate is going to be, as it says, first order in A, so it's just A to the first power, and second order in B, B to the second power. You would just, put that as powers. And that was the answer. Now, question 3. The overall order of a reaction is 2. The units of the rate constant for the reaction are blank. Now, I gave a little cheat back when we were in class with this little format where N up here represents the entire reaction order or the overall reaction order. So if we plug that in, 1 over M2, because reaction order is 2 here, minus 1 times S, that's 1 over MS. And that's the answer. Question 4. As the temperature of a reaction is increased, the rate of the reaction increases because when temperature increases, kinetic energy increases. So when kinetic energy increases, the reactants move faster. If they move faster, they collide more frequently. And that's that. Activation energy is only lowered for this one. It's only lower when you have a catalyst. They don't start colliding with greater energy per collision with less frequency. That doesn't really make sense. So the only answer that makes sense is the bottom one. Number 5, if a rate law is zero order in reactant A, doubling the reactant concentration blanks the reaction rate. Well, zero order means that changes in concentration have no effect on the rate. So, by definition, this is the only possible answer. Zero order means that if A's concentration is doubled, then nothing happens to the rate because it's zero order. It does not affect the rate at all. 6. The minimum energy needed to initiate a chemical reaction is, definition, activation energy. In our reaction diagram, that is this amount here from reactants to the top. That is your activation energy. Number 7, which energy difference in the energy profile below corresponds to the activation energy for the forward reaction? Okay, so we just kind of define what activation energy is. It's the energy your reactants need to get this reaction going. So it's this energy here. So the answer is X. Question 8. Which change will increase the rate of the reaction between I2 and H2 in the reaction? I2 plus H2 goes to 2HI. Choose all that apply. So we're looking for what will increase the rate. we should know that adding a catalyst will increase the rate. Heating something up increases how fast things react. And that is it for this problem. If we add iodine as one piece rather than several pieces, that slows it down. Remember your laboratory we did with the Alka-Seltzer tablets. When you had several smaller pieces, the reaction was much faster. So this part is faster. If you decrease the partial pressure of hydrogen gas, that does not make things faster. Increasing pressure would make things a bit faster. So just these two applied. Now, our first quantitative question. Using the data below, find the average rate of disappearance of A from 80 to 160. Some guys missed that 80 to 160 time interval there. So a flask is charged with 0.1 moles of A and allowed to react to form B according to the hypothetical gas phase reaction here. The following data is collected. We're looking at 80 to 160. Now we know the disappearance is the change in concentration of our reactant over time. We just simply fill this in at this point. So change is final minus initial. This is my final. That's my initial. And these are the units or moles. And divided by final minus initial. And we get -3 times 10 to the -4. So yeah, just like that. Question 10. We have 2A plus B goes to C plus D. The following results were obtained when the reaction represented above was studied at 25 degrees Celsius. So we have all this data here. Write the rate law for this reaction. Okay, so we have to look where things are constant. There's a couple areas, but let's look where B is constant. So B is constant here in trials 1 and 2. So that means we study A. A goes from 0.25 to 0.75. Here, that is an increase by a factor of 3. So we see what happens to the rate. The rate goes from 4.3 times 10 to the -4th to 1.3 times 10 to the -3rd. That is also an increase by a factor of 3. So that means in your rate, A is going to be first order. Now B, we want to look where A has stayed constant. So A is constant nowhere, but we can analyze what happens here. We know, let's look at 2 and 3. So those are easy numbers for A and B. As A goes from 0.75 to 1.5 for A, that's an increase by a factor of 2. We look at what the rate does. The rate goes from 1.3 to 2.6. That's also an increase by a factor of 2. But hold on. B was also changing. So B went from 0.75 to 1.5, but this didn't seem to matter. We know that A is first order, as we just pointed out down here. If A is first order, this increase by a factor of 2 here should reflect an increase by a factor of 2 in the rate. So check, that fits the build for A, for substance A. Now with B changing, we would think that this would have an effect on the rate too, and that this rate 2.6 would be even higher. but it's not higher. So that means that B did not have any effect on the rate, making B zero order, which means that is your rate law, because B to the 0 power is just 1. Okay, number 11. Number 11 stems from this. It says, using the same information, calculate the value of the rate constant. Now my rate constant is K. So all I do is take the information in the problem here. I can do any step I want. I'll use reaction 1 or experiment 1. And I plug it into my rate law, which I just found here. So I plug in for the rate, 4.3 times 10 to the negative 4th equals K, and A is 0.25. I solve for K by dividing 0.25 by both sides, and I get 0.0017. And now some people might not understand what I did there, just in case, do that. And this question, you did not need to put the units there. But if you did, gave you some points there. If you didn't, you didn't lose points either. Okay. So, yeah, that's K. Question 12. Consider the two-step mechanism for the decomposition of H2O2. Now here we have a two-step process. And in this process, all we're looking at is trying to figure out what these are by definition. So is it a product, a reactant, an intermediate, or a catalyst? So since I minus is present in the beginning and at the end, it is a catalyst. So we start with it and it's spit out at the end unused, essentially. And since O minus, IO1 minus, it's produced and then used up. So produced here, used here, that is an intermediate. So those would not show in your overall complex reaction. So a complex reaction, we have H2O2, H2O2 as our reactants, two of them, decomposing into two waters as products, and an O2. So, reactant, product, product. That's the answer. So consider the two-step mechanism for the decomp of H2O2. Again, write the rate law. Now we said in a multi-stepped mechanism here, your rate law is based on the slow step, and the slow step only. So we look at the slow step, and we know that rate equals K times my reactants, which are H2O2, and I1 minus. Now we can't write M and N here based on data, so we simply use molecularity. This is one molecule here, one molecule there. They're different, so we have a 1 and a 1 essentially as our powers. And this is your rate law. There's nothing more than that. You have to use a slow step. That's all I was testing here. All right, gentlemen, hope all this makes sense to you. If you have questions on anything further, then please reach out and ask. Adios.